And so we begin the unit on torque. During this presentation, be sure to pause playback whenever you need to pause to think about questions that are asked or to work problems or to just catch up in your note-taking. So hit pause anytime, and of course you can rewind, etc. These are the objectives for this unit on torque. You can read those for yourself. The second one on units, the SI unit for torque is the Newton meter. That's what N.M stands for. And the imperial unit is foot-pounds. So these are the learning objectives that we have for this unit. At the end of the unit, you'll see these assessment questions again, in which you need to be able to calculate torque and to calculate it in different situations, to be able to work with both the SI units and the imperial units, and also be able to determine the sign of different torques and for net torque. So here are some terms that you will learn. The last one, line of action, is also known as line of force. Here is an equation for calculating torque. The symbol for torque is the Greek letter tau. That is the lowercase letter tau. And in English, the way you spell it, well, first of all, this is kind of how I make it when I'm writing it. And that is T-A-U. So it's the Greek letter tau, the lowercase letter tau. And it is equal to the moment arm, also known as lever arm, R, multiplied by an applied force. So consider the box depicted on this slide. Now this is a top-down view of a box on the floor. If two forces equal in magnitude are applied to the box as shown, what is the net force? And will the box move? Pause the playback in order to ponder the answers to these questions. As you have no doubt deduced, the net force is zero. You have 100 newtons pushing in opposite directions on the sides of the box, and so they add to zero. But will the box move? Pause the playback to think about it. You probably intuitively knew that the box would rotate. This rotation is caused by torque. Remember that torque is the product of force and a moment arm. And the moment arm is the perpendicular distance from the pivot and to the line of action. So it's the perpendicular distance from the pivot to the line of action. And we'll see more about that later. Remember, when we studied studied circular motion, we said that the linear variables and the angular variables for displacement, velocity, and acceleration were analogs of each other. Well, torque is the rotational analog of force. So force is in the linear world, torque is in the rotational world. And remember, torque depends not only on force but also on the moment arm. So the bottom statement on the slide says that the same force can produce different torques. That's because you can change the location of the force and therefore change the value for R, or the value for the moment arm. Let's consider opening a door. Notice the hinge on the left of each door. For each door there's a force applied to it, forces A, B, and C, and they are all 50 newtons. The question is, which is more effective at opening the door, A, B, or C? pause playback to consider your answer. I'm fairly certain you chose force A. You probably have a feel for this. But all three forces are equal. Why is force A most effective? Pause playback to think about it. In this diagram, the line of action is labeled for you. It is the imaginary line on which the force lies. So you see the force on the right, and the vertical line through it is called the line of action. The moment arm is labeled as R, and it is the perpendicular distance from the pivot point to the line of action. The pivot point in this chapter is also referred to as the center of rotation, or the axis of rotation. So the perpendicular distance is labeled, and it is perpendicular from a vertical line going through the force and a vertical line going through the pivot point. But what if the force was not perpendicular to the door? What would be the moment arm then? I'll draw it for you. So I'm going to get rid of what's drawn here first. And so let's say the force is at an angle kind of like this, except that's not an arrow. There. So the force is kind of like that. Well, the first thing is you need to draw a moment arm, or not a moment arm, you need to draw a line of action that goes through that force. And so I'm going to attempt to draw a line of action through that force that is parallel to it. Not bad. Okay, so that is the line of action that goes through the force, and I'll label that for you. The perpendicular distance is the moment arm. So I need a line that goes through the pivot and is perpendicular to the line of action. So that looks like that might be fairly perpendicular. And so that would be the moment arm R. And so that is what is meant by the perpendicular distance from the pivot to the line of action. And that's how you determine it when the force is not perpendicular to the door in this case, or not perpendicular to the beam, or whatever the object is that the force is being applied to. Okay. So recall that equation for torque. Torque is the moment arm times force. Let's give some values to these. If the moment arm is half a meter and the applied force is 50 newtons, then what is the resulting torque? Pause playback to do the calculation. .25 Newton meters. If you did not get the correct answer, pause playback to review your work. So again, the units for torque in the SI system are Newton meters, and in the English system or the imperial system, foot-pounds. Okay, now go to page 238 in the electronic textbook. Here you can explore this equation for torque further. This is what the calculator looks like on that page. And you see the blue boxes in the lower left corner labeled A, B, C, and D? Those are practice problems. Try those in addition to the one that is on this slide. Enter the numbers for torque and force. In this case, we have torque of 480 newtons and a force of 60 newtons. Use the calculator to get a feel for how the variables are related. Pause playback to work these problems. And while you're pausing the playback, you can switch over to another window in your browser to open the ebook and go to page 238. If you don't want to go to the ebook, then do this on paper with a physical calculator. "8 meters. If you did not get the correct answer, pause playback to review your work. So for this one, set the moment arm to 0 and set the force to 50 newtons. What would the torque be? Pause playback to work the problem with the calculator. Remember, the moment arm is the perpendicular distance from the pivot point to the line of action. The resulting torque in this case is 0 meters. Since you said that the distance for the moment arm is 0, the line of action, and therefore the force, passes right through the pivot point. Therefore there is no torque and no rotation. So think about it. If you're trying to open that door by pushing on the door right where the hinge is, you would not be applying a torque. Even though you could press as hard as you wanted to, the door still would not open. So just as linear motion has a sign positive and negative, we usually take motion to the right to be positive and to the left to be negative, or vertically straight up is positive and straight down is negative. Torque has a sign as well, and we take the counterclockwise rotation to be the positive direction and the clockwise rotation to be the negative direction. And we've already seen this in our study of circular motion, so this is just a reminder. Consider the disk subjected to two forces. Think about the sign of torque for both of these forces. What is the sign of the torque produced by the force labeled F? Pause the playback to think about the answer. Well, this force is trying to make the disk turn in the clockwise direction, which is negative. Therefore, the torque that it produces is negative. What about the other force, 2F? Pause playback to think about your answer. Well, it's also trying to make the disk rotate clockwise, so that's the negative direction. So force 2F will also produce a negative torque. Same answer for the same reasoning. Here are three beams that have the same force applied in three different places, but the pivot point is also changing, the center of rotation. Pause the playback to study the slide. Do you understand the torque calculations? In the first one, the 10 Newton force is applied upward at the right-hand side. So I'm going to draw this one. So in this first one, the 10 newtons is over here. The pivot point is over here. And there's a distance of 2 meters separating the two. The perpendicular distance between the line of action and the pivot is 2 meters. So the torque is going to be the product of the force and the moment arm. So 10 times 2 is 20. And since it's trying to make it rotate in the counterclockwise rotation, or direction, that will be a positive torque. For the second one, still 10 newtons, but it is now 1 meter from the center of rotation. So the torque is the product of 10 and 1, so that'll be 10 Newton meters. It's also similar to the one before. It's also trying to make the beam rotate in the counterclockwise direction, so the sign is positive. For the last one, the 10 newtons is on the other end of the beam, 2 meters away from the center of rotation. So the torque that it creates is 20 Newton meters, just like the first one. However, it is trying to make the beam rotate in the clockwise direction, which is the negative direction. So the torque that it produces is negative 20 Newton meters. Remember that torque is moment arm times force. Take a moment to confirm the torque calculations that are already done for you on the slide. Make sure you understand the signs of each torque. For each force, ask yourself what direction it would tend to make the beam rotate. This will help you understand the sign for the direction of the torque. Now add the 3 torques. What do you get? Pause playback to think about this. The beam will not rotate because the 3 torques add to 0. There is no net torque, therefore there is no rotation. Remember we said torque is the angular analog of force? Force causes linear acceleration. Torque causes angular acceleration. If there was a net torque, there would be angular acceleration. But in this case there is no net torque, therefore there is no angular acceleration. But that's a topic for later. Now let's take a look at those assessment questions. Pause playback to work this problem. If you did not get the correct answer, pause playback to review your work. Pause playback to work the second problem. If you did not get the correct answer, pause playback to review your work. Pause playback to work the problem. If you did not get the correct answers, review your work. This is the end of the torque presentation.